All right, welcome back. So we just finished talking about how do we connect these dots to avoid plotting points, right? Because yes, you can absolutely plot what if when x is 1, what if when x is 2, what if when x is -1, what if when x is -4 or -2.5. But you should, from just these 3 points or these 2 points in this hole and your asymptotes, you should know what it looks like. So let's logically talk through this. Again, to connect the whole to this point, it just makes sense to do this. And then you're going to be getting asymptotically close to y equals 1. And then here, again, I'm not going to at any point turn around and cross my y equals 1 because I already showed it's never going to cross that line. So the only thing that makes sense to do is for this to go up, 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 right? Up toward my asymptote. Now again, if I'm going up on this side, ding, 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 that's my picture. That means I have to be headed down on this side because again, I had an odd multiplicity in my denominator. You could also and should also get that from here. I've got my y, my x-intercept here. So the only way for it to make sense is for me to then get asymptotically closer this way, right? I wouldn't be up here because I'd have to cross that asymptote to get here. And again, we showed the graph never crosses the asymptote. So that's what my function's going to look like. So let's look at our next example, B. All right, y equals x cubed divided by x squared minus 4. So again, let's step through our process. First, domain. All right, factor the denominator. That's going to be x plus 2x minus 2. So my domain is x cannot be plus or minus 2. Are either of these going to be wholes? No, there's no simplifying to be done here. So there's no wholes. So I've got two vertical asymptotes at 2 and at -2. So if you've got a grid, go ahead and draw those in. You can see that I drew those in green right here. -2 and -2 and +2. X equals -2. X equals +2. Are my vertical asymptotes. And then, right, they're both going to have opposite directions because, again, they both have an odd multiplicity in the denominator. So that's going to be helpful and good to know. And then your x-intercept, right, where do you have 0 in the numerator? At 0, 0. And so that's your y-intercept. So I put a nice big y and x-intercept right there at 0, 0. It's got multiplicity 3, so it's going to cross, and it's going to cross kind of like a cubic, right? Either like this or like this, depending on which direction it's coming from. So what's the end behavior going to look like? Well, in this case, my degree in my numerator is exactly 1 more than the degree in my denominator. So that means I'm going to have a slant asymptote. So do the long division, right? I'm going to get x times x squared minus 4 is x cubed minus 4x. When I subtract, that goes away. When I subtract, this is going to become a plus. So I'm going to have 4x. That's my remainder, right? There's nothing I can multiply by x squared to give me 4x. So this is just x plus 4x divided by x squared minus 4. So to find your slant asymptote, you ignore the remainder part and you just take the linear part. So y equals x is the equation of my slant asymptote here. So I drew that in. And all that means has nothing to do with what's going on in the middle. Again, that's end behavior. What's happening at the extreme ends when x is going toward infinity and going toward -infinity. So do we cross this slant asymptote? Well, clearly we crossed it right there at the origin, but do we cross it anywhere else? How do we know? Again, set your slant asymptote equal to your function. So x cubed all over x squared minus 4 equal to x. Well, so multiply this on both sides. So x cubed is equal to x cubed minus 4x. So if you subtract x cubed, you have 0 is equal to -4x. That only happens when x is 0. So the only time you're going to cross this non-existent line, this asymptote line, is at x equals 0. So then all we have, asymptote, asymptote, slant asymptote, and that point right there. Okay, you do need a little bit more. So even though I don't like plotting points, let's plot a few, right? So if I were to plot 1 over here, if I plug in 1, I'm going to have 1 over 1 minus 4 is negative 3. So 1, right, negative 1/3. Symmetrically, what kind of symmetry is this, by the way? If I plug in negative 1, I'm going to have negative 1 over negative 3, or positive 1/3. Yeah, what kind of symmetry is that? That's going to be symmetric about the origin. That's an odd symmetry. And it's true, if you plug in negative x, you're going to get negative up here. That's going to be the same. So we have odd symmetry. That is also something worth noting. Right? And so let's think about this. I know I'm going to be doing this and this here. So what, and that kind of corresponds with my cubic crossing that I was expecting through this 0. And so what makes sense? Am I going to turn around and cross the x-axis and have another x-intercept to then head up? No, I'm going to go down. Likewise up here, am I going to turn back around and go down? No, I'm going to go up. So that's what's happening in the middle. And again, since these asymptotes have odd multiplicity, so to speak, if I'm going down on this side, I've got to be headed up on this side. If I'm headed up on this side, I've got to be headed down here. And so again, plot one other point. I went ahead and plugged in 3 and negative 3, and they are giving me negative 5.4 or 5.4, so I plotted those appropriately. And again, this is where you're just going to, at some point, then start asymptoting towards this slant asymptote. So that's a nice rough sketch right there of this rational function. Okay, one more, and then we'll do something a little different. So in this case, I've got 2x cubed minus 2x squared minus x plus 3 all over x minus 2. Again, your domain is x cannot equal 2. Is that going to simplify out? Is it a whole or is it a vertical asymptote? Well, okay, so I use the factor theorem, or I guess technically I use the remainder theorem to help me determine if x minus 2 was a factor of this polynomial up top. If I plugged in 2, I got not 0. So it's not a factor. So it's not going to be a whole. No whole. So x equals 2 is a vertical asymptote. Right, like that. All right. Does this factor at all? Do I have any zeros? I mean, it's a cubic. It should have at least one real 0, right? Please be a nice real 0, right? So I tried 1. No. I tried negative 1. Success. So negative 1. Ooh, let's write this correctly. So x minus negative 1 is x plus 1, right, is a factor of my numerator. I wrote it correctly here. So x plus 1 factors out. Right? And how do we figure that out? I did my synthetic division over here. 2, negative 4, and 3 are the coefficients of what's left. All right, so what are my x-intercepts? Negative 1, 0, which I plotted right there. And it's got multiplicity 1, so it's going to cross my x-axis. And then this guy, if I set that equal to 0, and I use the quadratic formula, I'm getting negative b plus or minus the square root of b squared minus 4 times a is 8 times c is 24. Whoa, 16 minus 24, that's negative inside my radical. That's not real. So there's only one real x-intercept. Right? The y-intercept, if I plug 0, 0, 0, I've got 3 over negative 2. So that's negative 1.5, which I plotted right there. So again, I've got my asymptote and my intercepts so far. My end behavior, again, here my numerator exponent degree, my numerator's degree is larger than my denominator's degree. So in this case, it's kind of nice. I don't actually have to do polynomial long division because I've just got x minus 2. I can use synthetic division and rewrite this as 2x squared plus 2x plus 3 minus my remainder here of 9 minus, that should be plus 9 over x minus 2. But again, when I'm getting the end behavior model, the remainder does not matter. I just ignore it. And so y equals 2x squared plus 2x plus 3 is my parabola, my asymptotic parabola, which means that my graph, whatever's happening as x goes to positive infinity and x goes to negative infinity, it's going to look like this parabola here, right? So rather than plotting, like at first, so what you can see is I put this in vertex form, and I was at first going to try to plot this, but again, my function is not going to look like this parabola near 0. It's not going to look like it near the middle. It's only going to look like it as it goes to positive and negative infinity. So really, you can almost just treat it like the end behavior power function to know what your graph is going to look like. So with just this much, if I'd plotted no points, what makes sense? How would I, or how could I connect my graph? Well, clearly, these points are going to have to connect, right? So maybe something like this. And then I'm going to be approaching negative infinity, right? It doesn't make sense to turn back around because I don't have any more x-intercepts, right? And then this, again, is just going to be, you know, going up toward infinity, and it's going to be eventually kind of curvy like a parabola. But so maybe it looks, you know, something like this. I don't know. And then over here, well, again, if I'm going down on this side, right, denominator, the multiplicity is 1, it's odd, so it's going to be in opposite directions. This is going to be doing something like this, and then again, looking again kind of like a parabola over here. Now, how high up is it? Well, that might be worth plotting, right? So let's say when x equals 3, if I plug 3 in, 3 cubed is 27, 2 times 27, that's going to be 54 minus 2 times 9 minus 18 minus 3 plus 3 all over 3 minus 2, which is just 1. So 54 minus 18, that's 36. So did I draw this anywhere close to scale? No, right? In fact, this should be significantly higher than how I drew it, right? It's going to be like up off the grid, like way up here at 336. So to give you a better picture too, here's what it looks like on our graphing calculator. And you can see how the end behavior is modeling and looking like our parabola when we scale things differently. All right. Then the last example that I want to quickly talk you through is, let's go back to our piecewise defined absolute value function, right? So the absolute value of x is x if x is positive or equal to 0, and it's negative x if x is less than 0. So using this, rewrite this not technically rational function because it's a piecewise defined rational function, sort of, right? Use this, rewrite this as a piecewise defined function. So we're going to have 2x minus 3 all over x plus 1 if x is positive, and 2x minus 3 all over negative x plus 1 if x is negative. So now what I did over here is, again, I've got linear over linear. If I rewrite this in a way that is more easily recognizable as I'm shifting and stretching and flipping my reciprocal function, right? That kind of works better for me. Negative 5 over x plus 1 plus 2 is what my numerator simplifies and works out to looking like. So again, I graph that in purple over here. It's going to have a horizontal asymptote at y equals 2 and a vertical asymptote at negative 1. The y-intercept is negative 3, 0, negative 3 is your y-intercept. And then over here, again, when I just did long division here, right, you're going to have negative 2 minus 1 over 1 minus x. I can factor a negative out, and I can rewrite this as 1 over x minus 1 minus 2. So again, this is just shifted right 1 and down 2. So right 1 and down 2. Lo and behold, they meet at that same intercept. And so putting it all together, I've got my 2 bits to graph. It's going to have 2 horizontal asymptotes, 2 different horizontal asymptotes. One at y equals 2 and one at y equals negative 2. The y-intercept is 0, negative 3. The x-intercept is 1.5, 0, which again, you can solve your top part for that. And what else can you tell me? Well, there's no vertical asymptotes, there's no holes because the domain is all real numbers because it's continuous. The range is from negative 3 inclusive up to positive 2 non-inclusive. And look, it's always concave down. So on your own now, go ahead and try some of these on your own. tell me everything you can and then sketch the graphs. And if you want to see some handwritten, worked out solutions, go ahead and look at the solutions I've posted on our classroom as well.